well today. I'd actually like to start off with a bit of a video to kind of encapsulate what our teams worked on and a bit of the personal drive that kind of got me here today.
I remember this car ride from when I was a kid. I always looked forward to it and where I would end up. On the long days when we can't get the model to run, or the brakes don't function, or when everything is just going wrong, I just think about my grandparents. Who would you see today if distance was not a barrier?
Thank you, everyone. So let's imagine for a second. Let's imagine we could transport from San Fran to LA in just under 30 minutes. From Toronto to Montreal in under 25. Or maybe you want to move from one side of the island of Bermuda to the other in just under 2 minutes. So, what stops us? Why can't we do this today? Well, there's something we've learned to live with, to deal with, something that is the culprit. It is drag. It is something that resists our flow as we move through these mediums of air or water. Okay, so let's look at some old forms of transportation, ways we've innovated technology, allowing us to expand, communicate, and share our ideas. Now, these technologies have great benefits in their own. You have the road, which is inexpensive. You have a rail, which can sometimes be environmentally protected, immune to the weather. You've got the air, which has a great advantage in speed. And then water, of course, is one of the most energy efficient of these options, moving goods and people over long distances. But then, why not take the best aspects of these, really take a step back and say, how can we use these and think about drag and really create maybe something a little bit different? And this brings us to the Hyperloop, something that's been using technologies for the last 100 years, integrating and combining them in absolutely new ways. Elon Musk came with a proposal, a Hyperloop Alpha, a way to feasibly integrate these in other ways. And the result came as a tube, a vacuum tube, a low-pressure environment, something that won't create drag. An air cushion, something to levitate on top of, minimizing any friction on the floor. And shooting this capsule at very high speeds with very little resistance to this energy. So, how do we build this? Can we create this cheaply, effectively? And that was the question that's been investigated in this project. So, thinking about just the track actually is quite and can be quite easily constructed. You could have prefabricated pylons placed a set distance away and put prefabricated structures within these pylons that would allow all the ground assembly work to be done with standard construction equipment. Once you have these ground structures, you're done the entire ground assembly. And all that needs to be done is build a connection, a bridge, and a structure between these pylons. We then create fabricated tubes, prefabricated, with the idea of putting solar panels on top, absorbing energy naturally and latently throughout the day. So these solar panels, they create an opportunity to allow the system to be self-powering, to have more abundant energy than it is required to operate, allowing almost 24-hour autonomous operation. And by using regenerative braking within the tube, you can actually regenerate a lot of the energy electrically as you slow down. And this brings us to the challenge. So Elon Musk, he realized this would be a big project. And he took a very different approach and decided to challenge the world and students and companies to say, how can we actually build this? And made it an open source idea, allowing us to work and collaborate with other people to create this. Now, he challenged to build the actual pod. He would, and his company SpaceX, would work on the tube construction. This way, teams could focus on making the pod much, much cheaper, accessible, and functional, so that the only real cost would come from the tubing. Waterloo heard about this challenge, and when I was told that this was something that Waterloo was going to try to attempt, I was 100% all for it. It sounded exactly down my alley, and my interests were all aligned. But we have a unique case with what we're doing here. And this is what allows us to do what we are doing. And this is the case of being boundaryless in certain aspects. Particularly at Waterloo, they have a unique unrestricted IP ownership, allowing students and any individual working with the school in this way to take their idea and have ownership and not have that obligation with the school. They want to support these ideas and grow them without having you feel blocked. SpaceX also made it open source, allowing everyone to work on it, to share ideas, and to continue to collaborate in new ways like never before. And then the rotational team environment. This is a very unique aspect of what we do at Waterloo. Because we are in a co-op program, we actually have to move between place to place or job to job between 4 months of school and 4 months of work. Now, this is an interesting dynamic that we have to deal with, as great talent and students might not be there the next 4 months. But it's great in that regard because we get new talent we've never had before. Every term, we lose about 60 to 80% of the team to swap with a new 60 to 80%. And this brings us to the first prototype, the Goose one. And just a little bit of knowledge about the Goose. The Goose is a very iconic symbol for Canadians and for particularly us in Waterloo. In fact, I think there happens to be more geese than there are students, as you can see from this image of geese going to class. So I think they really are kind of iconic in the area, and we felt obligated to represent it. And this comes to our first prototype, the Waterloo Goose One, a levitating Hyperloop that can go through with minimal drag and demonstrate the technology. Here we have the Aircaster levitation, a way to lift on a small cushion of air, only about 1 millimeter thick. Eddy current braking, a way to use magnets to slow down without physically touching the rail, allowing for no wear and tear, allowing for no heating on the pod. A redundant friction brake system to make sure that we have a mechanical fail-safe when things go wrong, for low speeds specifically. A lateral control module, a way to stabilize on the rail with contact. And a drive mechanism, a way to drive through and taxi through the tube as necessary if emergency stopped or if other maintenance was required. And finally, a geodesic shell, a way to deal with the compression waves of the air better, a way to interact with a good structure for our pod. And this brings us to competition 1, and a place where we actually got to demonstrate this technology and work with other teams to see it as a reality. This was the first test track we created. It was a 300-foot track, allowing us to test at low to medium speeds. It probably took about 7,000 cups of coffee, but the students pulled it together, and we put it in pieces into a reality. Now, this is a few moments before, actually about a week before we had gone to competition, and the team was finally assembling the last parts of the pod, bringing it in to a nice opportunity to demonstrate everyone's hard work. We made it to competition, we worked together, and we demonstrated what our design would have been. Now, something unique happened at this competition, something I didn't expect on this level. And what happened was, because of the open source nature of the project, instead of everyone concealing their designs and being scared that everyone was going to take their ideas, people were open. People shared what they struggled with. People shared what they were doing now. And insight blew up into everyone's minds. Everyone felt like they had now learned this new set of standards and a new set of practices that would work better for the pod. Our team has now grown for the last 2 years, rotated, moved, and different hands, almost 300 hands of students have worked and passed the torch onto this pod. I now bring you to the Goose 2, our latest design, our way of actually improving upon what we learned, building upon our new talent and our rotation, and creating our next iteration for competition 2. It comes with a carbon fiber shell, as we had rotated students that happened to know more about carbon fiber, a unique trait of our group. We added more suspension into the levitation module, being able to deal with inconsistencies in the track or vibration at high speeds. We added a simple single braking system, making it mechanically fail-safe, taking aspects of both, making it lighter, simpler to build. And we improved our lateral control module in a way that needed no contact. We found that when you were moving these at 100 meters per second, they had a very high chance of deteriorating or melting away. We needed no contact to really achieve the high speeds we were hoping for. In fact, these wheels, what they have is they have magnets embedded inside of them. Magnets that essentially allow not only lateral stability, but thrust. We can actually now counteract the drag that we are generating, or even if it is very minor, and maintain a relative velocity as we go through the pod. This brings us to our concept of the future, the Goose X, the way to connect cities in the real way. This would be an experience allowing humans to really get the most out of how they can connect, how they can transport, and how they can eventually eliminate this barrier. I want to end this with a bit of a message, and I think Waterloop in itself has brought together a bit of this idea of creating open source and working with different disciplines and different ideas. By allowing this idea to be unrestricted and boundaryless, it has allowed the technology to accelerate faster than anyone's predicted, and it's allowed people from around the world to bring the best ideas together. By creating less of a barrier, we can now make sure that people are now interacting directly. Just as Dr. Susan had talked about. The oxytocin. This aspect, as it increases as you interact with other people. Truly being in person and creating less of a barrier of distance will allow us to really establish better connections with each other. I want to thank everyone who's helped us get to this point, and I want to thank you for listening.